Okay, so to recap, you're in the jungle, you hear a noise, and you know it's one of these animals, and now you want to say, what is the probability that it is a lion? Well, let's say you've been in the jungle for 10 years, and you know that for the past 2,000 times, every time you heard this sound, you went there and checked which one it is and recorded it. And so out of the 2,000 times, you found that, say like 200 of them was lion. And so you just say that the probability of a lion is just the fraction of the times that you found the lion. So it's 200 over 2,000, and that's 0.1. And you do that for all of these, and you say this is 0.1, this is 0.1, maybe this is 0.2, and this is 0.3, or 0.2, and that's 0.1, and that's... So they all have to add up to 1 because the total number of times is 2,000. So that's 2, and that's 4, that's 6, and so that would be 0.3. And the reason is they have to add up to 1 is that out of the 2,000, it's either this or that or that or that or that. So if you add everything up, you're going to get 2,000 and then divide that by 2,000. And that would give you 1. So that's the first basic principle of probability, that all the probabilities of everything have to add up to 1. Because these are, otherwise there would be another option that you didn't count. And then you can ask, what is the probability that it's something that would eat you? That's important. Well, it's lion, that we already said that was lions and ants. So you have to add up the probability from each separate outcome. Because let's say it was 200 times atoms plus 100 or 200 times ants over 2,000. That would be 0.1 plus 0.1, which is equal to 0.2. So you just add up everything from all the separate ones. Okay, so now we want to do something else. Now you're not in the jungle anymore, and you're back in town, and you want to play pool with your friend. And your friend, since he just came back after a long absence, he's going to arrange the pool table for you. So he's going to pick out the balls and put them on the table. And he's doing it one by one. So these are the options. So for what he can pick: 1, 2, the first ball, the second ball, third ball, up to 15. So he's picking them one by one, putting them on the table, and somehow, surprisingly, he tells you that, oh look, I just picked them out at random without even looking, and when I looked at the table, I found that I picked 1, 2, 3, 4, and 5. Okay, but that's weird. Like, it's you think this is not very probable, so you don't know if you should believe him or not. So in order to see that, in order to determine whether you should believe him or not, if there's a million other ways that he could have done it, you probably shouldn't believe him. If there's a billion, you definitely shouldn't believe him. If there was 10 ways that you can pull out the balls, then maybe this is one of them, and it's not that improbable. So that all depends on what the space of all possibilities is. And the thing is, there's so many possibilities here, you can't really list them all. So the first one could be this. The second one could be maybe 5, 4, 3, 2, 1. Another possibility is maybe 15, 14, 2, 6, 8. So any 5 of the 15 you could pick out in any order. So there's so many of them, and you don't want to list them all. But what you do want to say is, each one of them has the same probability. There's no reason that this is more likely than this. So this has probability P, this has also P, this has also P, And we don't know what P is. But, like we just said, the sum of all these P's, 1 plus the second one plus the third one, up to the last one, is equal to n. That's the total number of possibilities times P. And that, because this is the entire set, it has to be 1. You have to pick some combination. So that means it's 1. And that means that P, whatever it is, it's 1 over the number of all possible outcomes. So what we're going to do is try to count. That's why probability is often just counting how many different ways that you can get something. So let's try to count. And this is a common kind of counting, which comes up a lot. So let's say let's think about how your friend did it. He picked out the first ball and put it on the table, and then picked out the second one, then the third one. And so if we want to count how many different ways he can do it, let's put these slots here. How many ways he could pick out the first one? Well, there's 15, because it could be 1, it could be 2, could be 3, up to 15. Could be any one of them. On the second trial, well, now there's 14 left. You don't know which 14 because you don't know which first one he picked. But for any one he picked, there's 14 left. So here there's 14 ways that he can pick it. So that would be, if the first one was 1, then the second one could be 2, could be 3, up to 15. If it was 2, then it could be 1, could be 3, and so on. So for each one of these, there's 14, 14, 14. So far there's 15 possibilities for the first one, times 14 for the second one. On the third one, there's 13 left for him to choose from. Then there's 12, and then there's 11. So the total number of ways that he could have done it is 15 times 14 times 13 times 12 times 11. Because for each one of these, there's 14 times. And for each 2 of these, there's 13 left. So this is actually a nice number, 360, 360. Okay? And so the probability now is 1 over 360, 360. And it's approximately, let's say, like it's almost 3 in a million. So if a million people were picking out balls and putting them on the table, then only 3 of them would get 1, 2, 3, 4, 5. So it's a very rare thing. You should be skeptical of your friend. So, however, let's say he didn't pick them all one by one. He just picked out 5 and put them on the table. So it's not that he did first 1, then 2, then 3, then 4. He could have gotten 1, 2, 3, 4, 5, and then maybe 5, 4, 1, 2, 3. Any other combination. So how many of these are there? Because if you know that, let's say there's 1,000 of these, then the probability of picking this set of numbers in any order will be 1,000 times this probability of just one of them. Remember, when you want the probability of many things, and they all have equal probability, it's just the number of those things times the probability of one of them. So to count these, we're going to do a similar thing. We'll have the slots, and then we'll say, what could be on the first slot? Well, it could be 1, it could be 2, it could be 3, it could be 4, it could be 5. Now, so there's 5 options. On the second slot, well, if you chose 5, then there's 4 left. If you choose 1, then there's these 4 left. There's always 4 left. but a different 4 each time. So here there's 4 left. And same here, there's 3, there's 2, and there's 1. So the total number of ways that you can rearrange these 5 around is 120 if you multiply these. Okay, so now the probability of having the set 1, 2, 3, 4, 5 in any order is going to be 120 over 360, which is still like 3 in 10,000. So it's still very unlikely. Okay, so I hope this was useful. The probability theory is used everywhere, especially in mechanics. You already know that just in the air around me, there's 10 to the 22 atoms just flying around. And they're flying around at random. You almost feel like there's no way you can predict anything or say anything about how they're moving. But when you use statistics and probability, as we do in statistical mechanics, you can actually just calculate what is the average density of the atoms, and you will get something definite. That's how you get thermodynamics. That's why we can predict what will happen if I heat up water. Even though water is composed of so many molecules, you can't even know what each one of them is doing. But you can always know that if the temperature is over 100, then it will boil. And that's because you're using statistics.